Well, that's a first. There we go. So we're recording. Great. Okay, so let's get back to the Sn1 and E1 and talk about the substrate and how the substrate can affect the rate of reaction. Well, remember that the first step of an Sn1 reaction is a loss of leaving group, and then it's followed by a nucleophilic attack. This is our rate determining step, and so the better the leaving group is, the faster your Sn1 or your E1 reaction is going to be. What did we say about leaving groups? We said the weaker the base, the better the leaving group. Where do you get a weak base? From a strong acid. And therefore, the, the, the conjugate base of the strongest acid is going to make the best leaving group. And so iodide is the best leaving group. It's better than bromide and chloride. And fluoride is the conjugate base of an acid that isn't strong. And therefore, fluoride is a poor leaving group. So again, you got to remember that that rate determining step is the ionization, the loss of leaving group, the formation of the carbocation and the halide. And thus, that is why the more stable that the halide is, the weaker base it is, the faster the ionization is going to be. Good leaving groups, something that we need to be fully aware of as organic chemistry students. Let's talk a little bit more about this carbocation and how stable this carbocation can be. I taught you that a tertiary carbocation is more stable than a secondary or a primary or a methyl. So based on that, the solvolysis reaction, which is a first order reaction of a primary or a secondary alkyl halide, is usually too slow to even observe. It doesn't even happen. However, besides tertiary alkyl halides, you can imagine this being organic chemistry, there has to be other substrates that can undergo Sn1, and the answer is yes. If you have benzylic or allylic halides, they can also undergo solvolysis reactions. Now, why would that be? Why can they undergo the loss of a leaving group even though they're not tertiary carbocations? And the answer is because you form resonance stabilized carbocations. If it's resonance stabilized, it has enhanced stability, and therefore if we have benzylic halides or allylic halides, then solvolysis or these first order reactions can also occur. Something that you got to be aware of. So you got to look out for benzylic leaving groups or allylic leaving groups. So it says here on the next slide that you should be able to judge. You got to be able to look at your substrate and say, is this going to be able to undergo an Sn1 or E1? Is it tertiary or is it benzylic or allylic? In general, again, a primary or secondary, forget about it. It's not going to undergo solvolysis, so don't worry about it. You don't form a carbocation that's stable enough. However, again, tertiary, allylic, benzylic halides can all undergo solvolysis. So you're going to end up with a mixture of Sn1 and E1, right? The first step in this reaction, we have a benzylic position. Remember that if you have an aromatic ring, right? If you have an aromatic ring and you have something coming off of it, this position, the first carbon off of the aromatic ring, this is called the benzylic position. So benzylic position, and therefore this is a benzylic halide, right? A benzylic substrate. This can lose this leaving group spontaneously. Why would that be? Well, I don't have a lot of room here, but if I pencil it in, you would form a benzylic carbocation that would look like this. And we can draw 3 more resonance structures where we show the delocalization of that positive charge throughout the ring. I'm not going to draw all of them, but I'll draw a couple like this, and then you could keep it going like this, so on and so forth, and draw more resonance structure. So because of that enhanced carbocation stability, it's able to undergo Sn1 and E1 reactions, and so we can end up with a mixture of the Sn1 product and the E1 product. Pretty crazy, huh? But it's something that organic chemists have to be on the lookout for. It's something that we all have to look out for when we're doing these kinds of reactions. So with that in mind, let's talk about the Regio selectivity of the E1 reactions. Just like in E2, you can end up with mixtures of products. You can end up with a Zaitsev alkene, a Hoffman alkene, and substitution products. So if you're doing an E1 reaction, it's pretty quick. The rule is this: it's always going to give the most stable alkene as the major one. Okay, so that's the rule. Don't worry about anything else. There's no exceptions for us. The most stable alkene, so this one here, which would be the Zaitsev product, is always going to be our major product. And so the E1 reaction is Regio selective. Okay, we're going to be able, or sorry, we're always going to get the Zaitsev as the major. The difference is this: you remember Zaitsev and Hoffman with the E2s? We could control them by using a non-hindered base to get the Zaitsev and a hindered base to get the Hoffman. With an E1, you can't do that. There's no way to change the ratio of Zaitsev to Hoffman. You just get what you get. There's no choice of base because you don't use a base. You just use your solvent, which behaves as a base. And that is why in E1 or in first order reactions, we can end up with so many different products. Check this out. If we look at this compound, there's a lot of stuff that can happen to this compound. It's a tertiary alkyl halide. We're in water, so we're not in a strong base. The first step would be loss of a leaving group, and you would form a tertiary carbocation. Okay? So hold the phone. You've got this beta proton. If you pulled that one off, that would give you this product. Then you've got this beta proton and this beta proton. And if you're thinking, well, aren't those identical? No, they're going to result in the cis and the trans. One of them is going to form the cis alkene. The other one is going to form the trans alkene. So how do you know which one is the major? Well, I told you that the more substituted alkene is going to be the major. And if you say, well, both of these are tri-substituted, which one is major? Well, this one is E and this one is Z. And you can see that the E is going to be less sterically hindered. And so that's why it is the major product. Now you are forming a tertiary carbocation, so there's going to be no rearrangements. And so after nucleophilic attack and proton transfer, you would form the substitution products. Wowie wow. That is a lot of different products that you can form, Mr. Dion. Absolutely it is. Do I need to be able to identify them all? Absolutely you do. Okay, it's just part of being in organic chemistry is to be able to identify all the components that would be formed in a mixture. It's part of just what we do in this class. Now, before we get into some practice, I have one more thing I want to share with you. I think it's not that bad. If you understood stereocenters, well, let's say you have a tertiary alkyl halide, like this here. This is a tertiary alkyl halide. And let's say you do your loss of leaving group. This is what's happening here. Well, if you have a tertiary alkyl halide, and the alpha carbon is a stereocenter, so this is a stereocenter, then you're going to go from a carbon that's sp3 hybridized to forming a carbocation, which is sp2 hybridized. What do we know about sp2 hybridized carbons? They're planar. So this is planar, and thus the nucleophile can come in and it can attack from either side. Therefore, we're going to get inversion of configuration, where the stereochemistry flips like the umbrella in a wind that we saw for an SN2, backside attack. But you can also get retention of configuration, where the nucleophile comes in on the same side that the leaving group was originally. All right, so recall that in an SN2, we got the backside attack exclusively. But again, now, since we're going through a planar intermediate, we can get both. You're going to end up with a mixture of R and S. But we usually end up with a little more of one than the other. Check it out. Even though you get a mixture, typically you get more of the inversion product than you do of the retention product. Why would that be? The reason why is because you've got to break the bond between the carbon and your leaving group. And while the leaving group is leaving, it kind of wants, it's kind of like, Celine Dion, like near, far, wherever, I just kind of miss, they kind of miss each other. You've got something that's negative and something that's positive, and they're kind of attracted to each other. And we call that an ion pair that are attracted to each other. And so it's a little harder for the nucleophile to squeeze in there before all the bromide leaves. And so normally we end up with a little more of the inversion of configuration than the retention of configuration, but it's usually close to a 50-50 mixture, only a little bit of a difference there. Well, with all of that information in mind, all about Sn1 reactions and E1 reactions. Let's see if we can solve a couple of problems. Do not be intimidated about this by all the information that we just covered. What you want to do is go over it, make sure you understand it, and when you see a problem on a quiz like this one or this one, what do? You take a methodical approach to solving it to see if we can figure out what the products would be. So let's start with 7.26a. Let's examine it. We've got a tertiary alkyl halide. So it's not going to undergo an SN2. We've got just a solvent. So it's not going to undergo an E2. So what have we got? SN1 and E1. How do I know I'm going to end up with both? Because they both proceed through the same intermediate, the carbocation. Let's draw that intermediate just for the heck of it. Draw the loss of leaving group. Oops, here we go. The loss of leaving group, like that. And let's draw the carbocation. So it's going to look like this. There we go. There's our carbocation. It's a tertiary carbocation. It's not going to undergo any rearrangement. So why don't we do the elimination products first? I can rip off this beta proton, or I can rip off this beta proton. Now, if you're saying, well, Mr. Dean, I thought you said there was two types of beta protons here. There are, but there's no cis or trans to speak of here because you have two methyl groups here. So we don't have to worry about cis or trans. We just have to worry about the Hofmann and the Zaitsev. If you were to pull off the red proton, you would make the double bond. Oops, you would make the double bond here. So let's draw that product. It would look like this, where you would have the double bond here, and there you have it. If you pulled off the blue proton, you would have the double bond here. So let's draw that. 1, 2, 3, 4, like this. And remember, there's no cis or trans to speak of here, so we don't have to worry about that at all. Could anybody tell me, would it be, which one would be the major product of elimination? Would it be the blue compound or the red compound? Not a trick question. Which would be the major elimination product, the blue one or the red one? Exactly. Thank you, Kiana. It's going to be the blue one, isn't it? Right. Thanks, Angel. Absolutely. We'll put here, out of these two, we'll say these are the E1 products. And we'll say that this one is the major of the E1 products. Okay, so what does the Sn1 product look like? Well, we have our same old tertiary carbocation, like this. Our ethanol comes in, does a nucleophilic attack. So we have our nucleophilic attack like this. We form an oxonium ion that looks like this, like that. It undergoes a proton transfer, so the ethanol is going to come and pick up that proton, this, and then we end up with our ether. So this would be the Sn1 product, would look like this. So this is our Sn1 product. And so if I just use that yellow highlighter, I end up with 1, 2, 3 products in this case. Any questions about that one? Are you with me on that one a little bit? Even if you're with me part of the way, it's going to have to be practiced. There is no way a person could just observe this and say, well, I got that down. I've got that down for the rest of my life. Okay. So why don't we take a short break? And what I would like you to do is when we come back is to try, or I'd like you to try this one during the break. We've got another tertiary substrate. So the first step is going to be the loss of the leaving group. You could try drawing the carbocation that's formed and then see how many elimination products you can draw and how many substitution products you could draw. I'll give you a clue. There's more than 3 products that are formed in this situation. So again, I'd like everybody to take a look at this one, try to draw all the products, and we'll come back in 8 minutes. So we'll come back in 8 minutes and give it a shot.